Hey, I'm Liang. I'm an assistant professor at UC Berkeley. So today I'd like to use five minutes to tell you about our investigation of intriguing object discovered from gravitational lensing, and hopefully we can learn something about star formation in very dense environments. I should emphasize that this work is led by my student Massimo, who did a lot of the impressive analysis work. So Massimo yesterday told you about the superstar cluster in the sunburst arc, but apparently this arc is very generous. There's another interesting object called Godzilla. I have no time to tell you why the nickname, but it has very intriguing properties. So first of all, it lacks the predicted gravitationally lensed counter images, which means that this particular image is probably highly magnified because of unseen perturber. So from that, we derive a lower limit of the magnification factor, probably 400 to larger than 400 to 600. But then, on the other hand, the flux is surprisingly stable. So there's no microlensing-induced variability, which would be inevitable if the system is made of a low number of stars. So that sets the magnification to be less than 1,000-ish. Here's the spectrum of Godzilla compared to the superstar cluster, the other superstar cluster. And Godzilla has, so we can summarize the characteristics in the following. So first of all, it has a continuum from UV to optical that is very consistent with the starburst. Second, it shows these stellar wind features from O stars. Looks like a young system. It has nebula emission lines coming from ions that are typically excited by stars, but not by AGNs. But then, on the other hand, it has somewhat weak hydrogen Balmer lines, and then some of the optical nebula emission lines are detectable, but they are somewhat surprising that they are weak. So, but most impressive is that for some of the UV doublets, the forbidden component is completely missing. So that says the electron density in the ionized gas is at least 10 to the 6. And then the spectrum shows nitrogen enrichment, and the nitrogen line is even stronger than the other superstar cluster. And finally, apparently the environment is trapping Lyman line photons very efficiently, so there are a lot of fluorescent lines detected. So what we did is we analyzed HST photometry and ground-based spectroscopy, and then do a global spectroscopic analysis and trying to determine the property of the nebula. And what we found is that the nitrogen is indeed highly elevated, but then there's also evidence that perhaps oxygen and helium are a little bit more than usual in the gas. So one important finding is that through this kind of global fitting, we determined that the ionized gas probably has a density 10 to the 7 to 10 to the 8. That translates into a very high pressure and also very high ionizing radiation flux. So the question is why the nebula is highly pressurized, why it doesn't explode. Well, one possibility is that maybe they are compressed by radiation, but the ionization parameter is not very high, so that seems not very compatible with data. The other possibility is it's confined by hot corona gas, but then there's a cooling constraint because that gas, even at millions of Kelvin, has to be very dense. So the cooling time becomes shorter than the dynamic time. It's thermally unstable. So it leads to a dramatic suggestion that maybe the gas is undergoing runaway cooling and then has condensed at the bottom of the gravitational potential, as I show on the right. So here's a picture here's a cartoon that suggests that maybe the nebula emission is coming from these individual bubbles that are blown by the old stars. So I guess that's, I have to stop now. There's a new JWST data that might help us further understand this object. So, thank you.